Sebastian is a chemist here at university. He always wears black, I must to say, and he always wears black.
Slides.
Okay, but he is not a pessimist, and so you are also a pessimist. Okay, that I did not know. So go ahead. And he is a theoretical chemist and interested in history.
Yeah. Thank you. Thank you for this invitation. Hi. We are going to speak about broccoli.
Broccoli.
Bear with me, okay? So this is my viewpoint on a project that we are discussing right now with Jeff. So the title of this talk is How Long is the Cost of Chemistry? For those that don't know, this is based on the famous title of Mandelbrot's article in Science 50 years ago, something like that. How long is the cost of Britain? The idea is that Britain, the Isle of Britain, has a certain perimeter which you can measure. But it strongly depends on what is the ruler you are using. If you are using a small ruler, you will have that. If you are using a longer ruler, you will have that. And the perimeter will be smaller, actually. Same island, but smaller perimeter. Longer ruler will be like that, even smaller. And longer, and longer, and longer, and longer. Britain will get smaller, the line of Britain will be smaller and smaller until you reach the size of the Big Bang. That's a great shock, right? It took me a couple of minutes when never mind. Okay, so let me give you some premises as a big introduction of all the topic I'm going to speak. First, revolutions must not necessarily overthrow ideas. Okay, you may agree, not agree with all these topics. These are mostly oversimplifications of revolutions in general. So I believe, most probably there are lots of people that wrote much more about this and thought much more of this, but I believe that there are more or less three types of revolutions. The destructive revolutions, which are mostly what Kuhn was interested in, the Darwinian Copernican chemical, where they really have to destroy whatever came before. For instance, Lavoisier destroyed the idea of phlogiston. It's actually chopping off the head of the previous paradigm. But then you can have constructive revolutions. Again, my viewpoint. Yeah. For instance, I believe that quantum mechanics is not a destructive revolution. Well, philosophically you can say that when they brought quantum mechanics, then Newtonian mechanics was kind of destroyed, but the main idea of Newtonian mechanics is still working. Just that it turns into a model, smaller model of something much bigger. So it's constructing over the previous stuff, or if you want, standing on shoulders of giants and all this story. And then you have disruptive revolutions. I may be wrong on this, I'm not a specialist on that, but I think that the development of antibiotics came ex nihilo, from nothing else. It was something completely new. Central dogma, maybe, I'm not a biologist. I think it is a kind of disruptive revolution. Also the instrumental revolution was something like that. It was based on some other stuff, but it's something that came almost from nothing. Okay, second premise, revolution are in the eye of the beholder. And that's a big problem we have here. As everything in philosophy, good definitions are very scarce. We actually don't have a proper definition of revolution, for sure not of what a paradigm is. There's a famous phrase that Kuhn itself defined paradigm in 20 different ways. Something like that. Masterman was the... I cannot remember who wrote it.
Yeah, you're right.
So, it is in the eye of the beholder. So I like to work in the Ikiwisi principle, which says, this is a judge in the US that in a trial said, I imply no criticism of the court, which was faced with the task of trying to define what may be indefinable. And perhaps I could never succeed in intelligently doing so, but I know it when I see it. I know it when I see it. Is the Icky-Wisi principle. You know what he was speaking about, right? Pornography. Yeah, he was trying to see, to define if a movie was pornographic or not, because the laws are different. So I'm not saying that we are going to do pornography here, but the same idea of the Icky-Wisi principle is everywhere, almost everywhere, I may dare say, in philosophy. And defining revolutions, to me, looks a lot like the Texas sharpshooter fallacy. You know, that you shoot to a wall and then you draw the blank. So I'm not sure if it's like that, but I see people that say this, that, and that are revolutions, those other are not revolutions, so I will define revolution according to this set of revolutions that I think they are revolutions, and that I'm not considering the other ones. So it's not a good way of starting. We need something. So my next premise is that one can choose a framework to define revolutions. Okay, and better to start with something, a test, some definition, something, and then work and check what is a revolution or not from there. So I took Siemens 13 characteristics because they are very comprehensive. They are not universal. Not everyone will agree with them, but they tend to take most of the words that are usually used in the literature anyway to define revolutions. So if you take all these ones, you see disappointment, crisis, discontinuities, incommensurability, understanding new ideas, anomalies, new taxonomies, new programs, new methods, to be analogous to social revolutions, having new organizations, new sub-disciplines, new educational methods, and testimonials. Okay, so I did in 15 seconds a summary of this set of characteristics. A revolution doesn't need to cover all of them, but if it covers most of them, there's a high probability that it was a revolution. Fourth premise, a state of revolution may be the standard. So, according to Kuhn and some others, revolutions are have to be very rare, if not they are not revolutions. But if you look at a lot of material, a lot of people doesn't actually think like that. As in this example, this is a paper called The Fifth Chemical Revolution from Norfolk Chamizo. Doesn't matter, just giving you an example. He thinks there were 5 revolutions in chemistry, starting from the first, from Lavoisier and Dalton. And I took all these dates when the revolution started, according to him, and when it finished, and it looks like this. Each one of these cylinders is a revolution. So being outside a time of revolution seems to be the outlier, not the normal thing, which kind of makes no sense. But anyway, if they are revolutions and they take so long, maybe we are almost always living in a state of revolution. Not always in your field, fine, but there's always a revolution brewing in. 5, revolutions might come in different sizes. And here's the key of this lecture. So, just for the sake of the argument, I'm not saying it is like that. I'm saying that revolutions can be bigger, smaller, and there is a continuum of that. But just for the sake of the argument, I will divide it, categorize it in 3 different boxes. Macro revolutions, which are the ones that everybody agreed that they were revolutions, that they cover whole disciplines, that they are large and conceptual and practical implications, blah, 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 like the chemical and atomic revolution, the quantum mechanics, etc., etc. Meso-revolutions, they are major changes, but in sub-disciplines. In sub-disciplines, and not in a whole discipline. Or maybe smaller, but multidisciplinary changes. Here, I would include the topics that you saw just now. The instrumental chemical revolution and the quantum chemical revolutions. I believe they were revolutions. but not in the whole field of chemistry as a big chunk of science, but in smaller pieces, in sub-disciplines. Still there were big revolutions, because we can have smaller revolutions, micro-revolution if you may, significant micro-paradigm changes in niche areas. For instance, density functional theory and NMR. Now I'm bringing DFT, density functional theory, because it's my field, and I want you to take this as an example of your field. It doesn't matter what you're doing in science, take this just as an example. Now, other topic, fractals, something new. You know what fractals are? No? Raise your hands if you know what is a fractal. If you don't know, if you are sleeping. Okay, very, very fast, I don't have much time. A fractal looks like this. Very beautiful figures. This is a simple equation, it's not very complicated, that when you draw it, it gives you a very beautiful figure like that. Now the small square, focus on the small yellow square there, because when you zoom that out, it looks like that. And if you zoom now, this yellow square, where is my laser here? Never mind. If you zoom that yellow square again, you will obtain that picture. And you zoom it again, and again, and again, until you zoom it orders and orders or orders of magnitude, and you take from there pictures that are actually looking very similar to the first one. Actually, this is infinite. You can zoom it out infinite times, and it will continue looking like this. Every one of these will be different, but they will all look very similar. This is political self-similarity. Okay? Bear that in mind. A simple, much simpler fractal is what is called the Koch snowflake. You take a triangle, you just put triangles in the sides. You get a Star of David. Right, now from there, you put smaller triangles on the sides. You get that. And again, and again, and if infinitely you do the same process and you obtain a fractal. You zoom out these structures and it looks like the big one, just self-similar. And here is the point. When you do this three-dimensionally, what you get is a Romanesco broccoli. If you see it has a kind of cone and cones going out, and from those cones micro cones, and then continues like a fractal. Yeah? So, a broccoli is a fractal. So my premise is science is a broccoli. I want to focus then on only that small part of the broccoli, of the whole world of science, and that small part is a small part of chemistry, a bit of physics as well, called density functional theory. Again, just an example of any other field that you may be working on. So this is part of quantum chemical revolution and part of chemistry itself. Now, when theoreticians bring formulas, it's not to show formulas. I'm not showing formulas. I'm showing off. You don't need to understand the formula, just see and say, wow. So before DFT, we know, according to Schrödinger, that H psi was equal to E psi. So this formula has everything. It's the answer for everything. I'm not joking. This is the answer for everything.
42.
So here we have the Hamiltonian and the wave function. The wave function is critical because, okay, the Hamiltonian is that in chemistry, for molecules. Everything is there. Everything is there. Okay? So there is a postulate in quantum mechanics that says that all the properties of a quantum system are determined by the wave function. If we have the wave function, we have all the properties of the system obtained from these equations. The problem was already known a very long time ago. Dirac told us in 1929, almost 100 years ago. The underlying physical laws are thus completely known, and the difficulty is only that they lead to equations much too complicated to be soluble. So we know the truth, we just don't know how to reach it. We don't know how to solve this equation. It's very tough. We know how to do it for a hydrogen atom, that's it. It's not much of chemistry, right? So then there were method approximations to solve this. The first one was Hartree-Fock method, where the equation looks very similar. You see, that was the previous one. This is the new one. Before we have wave functions, now we have orbitals, which are the wave functions of single electrons. And there is an equation very similar as the previous one, which you don't need to know, that doesn't matter. But if we solve this, and there is a method to solve this, iterative method, we have a method to solve this, we have a method to solve Schrödinger equation. Fantastic. And this is really fantastic. It has this approximation, which is called the mean field approximation, has a 90% accuracy. 90% accuracy, it's fantastic.
Not for quantum physics.
No, well, you have a 4.0001.
Yes, 1165.
What? Now you will hear why. There was a famous theoretician, Coulson, that in the 50s, 60s said, we have a problem here. Computing, calculating at that time, the reaction, the energy of reaction, it's like trying to weigh the captain of a ship as the difference between the ship plus the captain minus the weight of the ship. So the 1% loss in accuracy of this method may mean that the captain will weigh 100 kilos, 1 ton, or minus 1 ton. It's problematic. Yeah, it's a kind of crisis, you may say. So here's very, very fast the table. These are numbers that I actually did at some point years ago when I was young. Yes, I just look young. I'm not young anymore. So we have a table of the time it consumes and the error of the method. Hartree-Fock has an order of n to the power of 4. That doesn't matter. Think about this as the size of the molecule. Yeah, n is the size of the molecule. So with Hartree-Fock we can do nowadays molecules, big molecules like that one. The problem is that the error is up to the roof. I call this a very complex random number generator. Hartree-Fock is almost useless unless you really know what you're doing. From the idea of Hartree-Fock, there were extensions based on virtual orbitals, doesn't matter. So the first one was called MP2 with perturbational theory. It has an order of magnitude heavier computation, so you can do, molecules of normal size, but not the molecules, the big molecules that we want to compute. And the error was much better, way, way better. Still not good, but way better. So we can do, at least with this method, moderately sized molecules with some error. Now you have methods such as coupled cluster, doesn't matter, it's the same idea but much more complicated, where it has a small error, it's fantastic method. Really, really accurate. The problem is that the computational time is enormous. You can do only very small molecules with this one. It's order of n to the power of 7. This is called the exponential wall. It doesn't matter Moore's law of how fast the computer will get in the future, because this will always win. You put another hydrogen and that's it. You cannot compute it anymore. So I would say that with this, we had a crisis. Not a big crisis in all chemistry. All chemistry didn't care about this. But the field of computational chemistry was a big crisis. Actually, people outside chemistry, outside computational chemistry, doing organic chemistry, inorganic chemistry, didn't want to share anything with computational chemists because we didn't have the tools to give them proper answers. So they just didn't believe in us. This, you may say, it's a disappointment, to be mild. Yeah. So here we have a couple of issues of revolutions, conditions for a revolution. Then, let's take this out. And let's start with density functional theory. Now, if you remember previously, we said that all the characteristics, all the properties of a molecule you can get them from the wave function. Density functional theory, and there are theorems to prove this, says that all the properties of a quantum system are determined by the density. There is a connection between the wave function and the density, but it's a completely different concept. It's different. It's not the same. So we can use the density to get all the information. How we get that? It's complicated. We have formulas. They look like this. Lots of integrals. It's still complicated, but it looks very different to the previous equation of Hartree-Fock. Very different. So the point here is that we have psi, the wave function, we have rho, the density. They give the same information, but they are not the same. Nothing to do one to the other. There is a mathematical connection between them. But in principle, they are just conceptually different ideas. So if you want to speak about incommensurability, you have it here. If you want to speak about discontinuity, you also have it here. When they brought the idea of using the density for all the properties, there was a discontinuity in the effect. So there were different ideas and understanding, for sure. For sure. It was conceptually different. Now, the first model of DFT was horrible. Was the same point, even worse than Hartree-Fock. Hartree-Fock at least says that molecules are stable. DFT, in its first version, said that molecules were unstable. You put two atoms together and they go away. It was a complete disaster. But then there is a story. There were levels, improvements, which is called the Jacob's ladder of density functional approximations. If you know the story of Jacob, he was sleeping and he dreamed of a ladder going up to heaven and the angels going up and down, right? Well, in DFT we have the same idea. The equations of Hartree-Fock going up and down with different accuracy until we reach the heaven of accuracy. It's not my metaphor. It's how we speak in the field. It's a lousy metaphor actually, but anyway, it's what we have. So doesn't matter what are all these levels. They are levels of accuracy, making the computation more complex, but not necessarily more heavier. So with all this, we have a new methodology. We have a new scientific program of developing more and more accurate DFT. We have a new subdiscipline inside quantum chemistry. And now, with these different ranks, we have the second level, it's basically the same computational time, and the accuracy is much better. And the third level, it was not important actually. The fourth level, we have a computational time that was more or less as Hartree-Fock. We can compute now this, but then with an accuracy that it was better than MP2. Still not that one, not capital, but we can compute with a relatively good accuracy really big molecules. Now let's see some other of the terms taking the Siemens 13 characteristics. New organizations, I cannot say that, but there are conferences exclusively about DFT. This one, the upper one, it's in San Sebastian if you want to go, very nice city. New educational methods, I don't know, but there are many books on the topic, exclusively on the topic. New lexicon ontology, I will just show you this table, comparing molecular orbital theory, Hartree-Fock and what was before, and density functional theory. There is one important term there which is called exchange, really important in physical chemistry. And the term for exchange looks completely different. And conceptually, they are different. For reactivity, people that are interested in this, in molecular orbitals we have the, for instance, Fukui frontier orbitals method to analyze the reactivity of molecules, and for DFT we have the Fukui function. Similar but conceptually different. orbitals, we have the mean field approximation to obtain the orbitals, and there we also have orbitals, but completely different. It's called the non-interacting constant orbitals. They look the same. They are not the same. Conceptually, they are different. So we have all of this. Now, anomalies. Did we have anomalies? I said no. There were no anomalies. This was a disruptive revolution. Remember what I told you before, that the it came from a crisis, but not from an anomaly. There was nothing that we couldn't explain. We just didn't have the computational power to explain it. Analogous to social revolutions, as in the French Revolution, no. No, this is not the French Revolution. We didn't cut the head of any king here. But as in the Protestant Reformation, if you want, yes. Well, we created a new denomination, and Catholicism is still there. I'm coming from Argentina, so I live with that 25 years. But now we have Protestantism. Was that a revolution? Well, you may say yes. Did they cut head? Well, they cut lots of heads now that I think of. Yeah, but that was different. Testimonial by observers. Well, it is me, meanwhile. We don't have much. However, okay, my point here is that testimonials by observers is the last point for a big revolution. When the philosophers take this and analyze this, it has to be something really, really big. You don't have many philosophers of science to take the small pieces of science and discuss that. So this is the last issue to understand what is a macro revolution, but not a micro revolution. Still, we have books on perspective in that one philosophical perspective in quantum chemistry, where there's a lot of DFT there, or it is going out right now a book about Walter Kohn, not Thomas Kuhn, Walter Kohn, Nobel laureate, he is the hero of DFT. His first biography book. He died some years ago. Okay, so disappointments, yes. Crisis, yes. He continued, yes, 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 yes. We have anomalies, no. That was not that kind of revolution. Taxonomies, programs, new method. Analogous to social revolution, which kind of revolution? Organization, subdiscipline, testimonials, not yet. I believe there will be at some point. Now again, this is DFT as a small subdiscipline. This is not chemistry. This is not a big revolution in chemistry. This is a smaller revolution. We cover most of the characteristics of a revolution, but as long as you are taking it for a small community. So in the end, DFT, as far as I'm concerned, passes the Seaman test and passes the Ikiwisi test. I know it when I see it. Now, okay, so very fast, macro revolution, I believe, will be the chemical revolution. Meso revolution will be the instrumental quantum. I have to think about this. It's not the final word. And then we have micro revolutions for each one of them, including DFT. And maybe there are nano revolutions inside DFT. Sorry. Like conceptual DFT, it won't tell you anything. But these are specific fields that are really revolutionizing the field of density functional theory itself. So the point is that revolutions are self-similar. The smaller and smaller revolutions are not the same as the bigger revolutions, but they are very similar when you look at it with the zoom out. They are a fractal. So, forgive me if you don't like this analogy, this is just a metaphor. I see Kuhn's kind of revolution as a staircase with jumps of revolutions and platforms of normal science. I think this is just a very simplified and very simplistic way of being science. That science, again, it is an oversimplification, but still it's a better model, works as the Koch snowflake, where we have macro revolutions, meso revolutions, and macro revolutions that are making all the things grow up like these stars. And if you want the analogy of Britain, that one has a very small perimeter because we were using a very, very long ruler. But if you take this example of fractals, then the smaller you get it, the better perimeter you will get. So to end this, the scale of observation makes the revolution. The discussion, I think it was not correct about saying was this a revolution or not, but was this a revolution of which size? So if we had normal science, and if you look at it with a magnifying glass, it will look like as a micro revolution. Now this is a great animation. Let me show this again. Yeah, look at this.
Yes,
Beautiful. So that's it. My main point here is that chemistry is a broccoli, science is a broccoli, life is a broccoli. So go and eat your broccoli. Okay, thank you.
Thank you, Sebastian. So, we have time for some questions.
If you don't like broccoli?
That's my wife. She can tell
I have
you
a
how much I
comment,
hate it.
not a question, a comment. I love your talk. I think you should give this talk in the chemistry department. I wrote that to you. But why broccoli, not dendrimers? We have fractal molecules that are real.
Yes.
And probably more tasty than a broccoli, I know.
Yeah.
More
Anyways,
beautiful.
yeah, it's okay.
I can.
Yeah,
Next
just
time.
change your broccoli for a dendrimer, and it's a wonderful talk. Just kidding.
Okay.
It was really, really nice. Thank you.
No, thank you. I'm curious, why don't you create your own criteria for revolution? Many of those are not very convincing.
First, because I'm not a philosopher.
No, but you're a chemist.
Yes,
You can
but
say-
I just took the words. I look in a lot of sources. What is the definition of revolution? There are no good no good definitions.
Yes.
But when I compare all of them, what they were saying, including Kuhn,
Yes.
yeah,
Sure.
and the list of, I took and wrote them down, the list of words, keywords they were using, incommensurability, crisis, new organization, blah, 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 and then I saw the paper of Chefa, and it was basically that.
Yes. But you heard so many lectures which had very different things to say about revolutions.
Of course,
There was no incommensurability. Of course, there was no anomaly, but also not in your case. And there was no disruption.
It's a criteria, it's not a definition. I don't think the chef.
You called it definitions.
Yeah, but I said that I need a framework to work with. So
Okay.
for this, it's a more or less a definition where if you tick most of them, you're probably with a revolution, but not necessarily all of them. And it depends on how much each one of them.
Yeah. And social revolutions you cannot test, and scientific revolutions you should be able to test.
That's not true.
No.
Social revolution in terms of the appearance and disappearance of disciplinary departments in universities and in industry. For example, before the quantum chemical revolution, before the instrumental revolution, there were not analytical chemistry departments, sub-departments in many chemistry departments. There was not medicinal computational chemistry. There's a whole chain. You don't know chemistry so much, I suspect, but I say that with due. I do. I live in that. And the world of chemistry has changed socially.
I know that, but I mean, let's say the French Revolution. We cannot. I'm not talking about the sociology of science. I'm talking about science, the content of science, the theories of science, and then you can test And you cannot test the theories of the French Revolution. You know, they wanted to create something and they created something very different. So I'm very skeptical. You can do a sociological analysis, but it's not science, it is the sociology of science.
Well, philosophy is not science.
No.
We were discussing that. That's why I hate philosophy.
I started to hate it too. But that's something else. But what I wanted, you know, factually, Darwin was not disruptive and Copernicus was not disruptive. You heard it also in several texts.
Copernicus, I think it was, in my definition, it was destructive, not
yeah, but disruptive, no?
No. Disruptive for me was something different. Destructive.
Yeah, but it was not. I mean, he used all the mathematics of Pythagoras and so on. He used a lot of things that were before, and the real change came with Kepler.
But then after Copernicus, you had or heliocentrism or Copernican mechanics. And if you take this one, you have to destroy this one. If you believe in this, then Copernicus was completely wrong.
Yes,
so in that sense, it was destructive, but I don't want to enter into that.
Historians usually say Copernicus started, but he was here with one foot in antiquity. But Kepler finally made the revolution, you know.
Okay, Kepler destroyed everything. I can find with that.
But with Darwin, you know better. Darwin, the theory of evolution was already quite accepted. And Darwin just stepped in and he made it very coherent.
No. Again, that was an oversimplification. I know very little about this. I'm not going to discuss, especially not with you.
But I discuss everything with you.
No, I'm joking. I don't want to make a thing about that because it's not my field. I'm not a specialist on that. I take this with the same hero in pinceta.
Okay, but if you do this talk again, just be careful.
I'm doing it with friends here. No.
Okay,
thank you.
Thank you, Sebastian.